tell who. All right. Let's go to page 68 when we're done. We are still talking about logs, and we still need to keep in our brains that logs and exponentials are inverse functions. All right. So they have their characteristics of their graphs have inverse relationships, and they also have a lot of characteristics in common. We looked last week at the general form of a log function, right? So we have this A, which is a vertical dilation, and A and B are constants. A can't be 0. B has to be greater than 0. So the base cannot be 0 and it cannot be negative, right? Something else we need to know. Domain, because now we have a vertical asymptote, goes from 0 to infinity. Range, negative infinity to infinity. For exponentials, these two are reversed because they are inverses of each other, right? So I'm going to remind you real quick, because we have room up here, what for exponentials, if I have this, if I have exponential growth, one way to get that graph would be like y equals 2 to the x power. If I have exponential decay, one way to get that graph is 1/2 to the x power. Right? The way in which it, whether it's increasing or decreasing, depends on the base of the exponential. The same is true for the log. Now, another way I could get this same graph would be to take this one and make a reflection in the y-axis, right? So there's different, like I said, there's one way to get it. And we're going to talk about a couple of ways for these logs right here. So for this log, this one right here, this could be y equals log base 2 of x. Okay. That would be like taking that 2 to the x and reflecting it in the line y equals x. This one way I could get it is y equals log base 1/2 of x. Okay. Now, if I look at what's written here, where a is greater than 0, that's true here, and b is greater than 1, that's true here. This says, we get this picture, when a is less than 0. That's not true for what I wrote, and b is greater than 1. That's not true for what I wrote. So there's more than one way. What this is saying, what is typed out, is saying basically we just take this and reflect it in the x-axis. And that is a way to get that. But if I write it like that, that's because a is greater than 0 and b is between 0 and 1. Okay. And then here, another way to get this would be if a is less than 0 and b is between 0 and 1. Like taking that one over there and just reflecting it. Okay. Now, is this function here, this first one, is this function increasing or decreasing? Increasing. Okay. Is it concave up or down? Down. All right. And that doesn't change. That's true for the whole time that the graph is there, right? And that's true also for exponentials, right? That's something else they have in common. Tell me about the rate of change. Is the rate of change increasing or decreasing? Decreasing. Why? The fun chart. Because the function is what? Concave down. Since the function is concave down, then the rate of change is decreasing. Is the rate of change positive or negative? Positive. So don't forget about the fun chart. Okay, if you need to write it down, write it down. Some of you may have it in your head, but not a bad idea to write it down. Since the function is concave down, the rate of change is decreasing. Since the function is increasing, the rate of change is positive. Don't forget about the fun chart. Okay, it could pop up anytime with any function. Right. But because logs and exponentials are always increasing or always decreasing, they have no relative extrema. They're not going to have any maxes or mins because they're not changing from increasing to decreasing or vice versa. Same thing with concavity. They're always concave up or always concave down, so there are no points of inflection. End behavior, we do have to change things up here a little bit for end behavior, because we know that as this is in general form. That means no other transformations or anything like that. As x increases without bound, the output values increase or decrease without bound. So as x approaches infinity, f of x is either approaching infinity or negative infinity. Those are your only options. But we had, for exponentials, we had a horizontal asymptote that changes to a vertical asymptote for our logs. And so since logarithmic functions have a restricted domain, they are vertically asymptotic. That's your $10 word for today. Asymptotic at x equals 0. That means they have a vertical asymptote at x equals 0. That's all it means. We can't head to negative infinity. We're not going to approach negative infinity because we have an asymptote there and it stops us from going. So as a result, your left-hand behavior will occur as x approaches 0 from the right. Remember the little plus and minus, that means from the right. So the limit as x approaches 0 from the right, okay, so if I scrolled past those other ones, but if we just kind of look at these, as I hit that vertical asymptote, or I don't hit it because you can't hit it, as I get closer to it, it's either going to shoot up to positive infinity or down to negative infinity. But as x approaches infinity, we're either going to infinity or negative infinity. Okay? Everybody okay with all that so far? All right. So let's look at these limits. We're going to write these left and right hand limit statements here. So my left would be the limit. And again, I'm not going to negative infinity. It says x approaches 0 from the right of f of x. And as I get closer and closer and closer to that asymptote, where is the function heading? Negative infinity. Then to the right, the limit as x approaches infinity of f of x, what's that going to be? Infinity. Any questions about that? All right. So this one, again, my left is being, I have a little barricade there at 0. So this is going to be the limit as x approaches 0 from the right of who? H of x. Make sure you don't call him f. His name is h. And what will that be? Infinity. Infinity. Good. And then the limit as x approaches infinity of h of x will be what? Negative infinity. Okay. Any questions about those? All right, so with the equations, I highly suggest you draw yourself a little picture, okay? And so I know the base is 3, that's greater than 1, so it's going to look something like that. The only other thing I have going on there is that 2. That's a vertical stretch. I don't have any numbers or scale on this graph, so will it change my bad picture? No. So that's it right there. So then I just write my statements from that. Limit as x approaches 0 from the right of who? G of x. What's that going to be? Negative infinity. And the limit as x approaches infinity of g of x will be infinity. Okay. Any questions at all? Okie dokie. All right, so now we're just doing concave up or down, increasing, decreasing. Is this function right here concave up or down? Up. Increasing or decreasing? Decreasing. Is the rate of change increasing or decreasing? Increasing. Why? Concave up. Because of our fun chart. Okay, because of our fun chart, the function is concave up, therefore the rate of change is increasing. Is the rate of change positive or negative? Negative. Function is decreasing. Or you can also do your little pencil test. You know, we're just like, look, if I drew in little lines, they're all have negative slopes on them. All right, we good with that? All right, B, concave up or down? Down. Increasing or decreasing? Increasing. All right, let's draw our little picture here. I like to start off with the parent function, which means I'm just looking at the log part of that. So log base 6 of x would look something like that. Okay, and it's fine just to kind of have that in your head, but I don't want to lose anybody, so I'm going to do this too. And then the 4 really wouldn't change my bad graph, right? But that negative does. That negative is going to reflect it across which axis? X. So it's going to look like this. So then this is the graph I'm also actually going with. This is concave up and increasing or decreasing? Decreasing. Okay. Everybody good so far? Any questions? All right. Now this says in example 3, selected values of several log functions are shown in the tables below. For each table, find the value of the constant k. Is this asking me whether or not these are logarithmic? No. Are these all logarithmic? Yes. So can my answer be it's not logarithmic? No. It's important to read the directions, right? So I know for a fact these are log functions. That means I should know some things about them. Bless you. I know that my outputs change additively and my inputs change multiplicatively, right? So what I want, though, in order just to know I can multiply, I need to look over here and make sure that my output values are actually equal length intervals, and they are. Okay, one is being added every time. So I've got equal length output value intervals, which means over here, where something's being multiplied. What am I multiplying by? 2. I can see that from going from here to here and here to here, right? So then what does k have to be? 4. Because 2 times 2 is 4. And then 4 times 2 is 8. And we good on that? Okay. All right. So now here, again, I look, and all right, I'm adding 5 every time. So I've got that. I'm good to go. Then over here, what am I multiplying by? 3. So what is k equal to? 2. 2 times 3 is 6. 3 times 6 is 18, and so forth and so on. Okay. Okay. All right. So you can look at any 2. I mean, obviously, I think we're going to look at these first. I mean, I would too. But if I put 162 over 54 and 54 over 18 and 18 over 6, I should get 3 every single time, right? Just obviously use the easier ones for yourself. So when I look at this here, okay, I have equal length input value or output value intervals. I'm adding a -10 because remember they change additively. But if I look, and I know it's a log, if I put 5 over 4 and 7 over 5, are those the same thing? No. But so I'm not going to put not logarithmic. It is logarithmic. But if you recall, and this was before Christmas, but when we were doing this with exponentials, we were very easily going, oh, we multiply, this is what it is. Then I threw one at you where I said, hey, this is exponential, but we couldn't multiply. We first had to look at the differences. Then after the differences, that's when it multiplied because there was a transformation in there. Does that sound remotely familiar? Okay, so since I know it's logarithmic, I need to look at the differences here. Well, 5 minus 4 is 1. 7 minus 5 is 2. K minus 7 is k minus 7. And 19 minus k is 19 minus k. Okay, see what I did there? All right, now I'm going to erase this orange right here so I have some more room to write so I can explain this better. So I'm just going to pretend like that wasn't there. All right, so now, okay, I did the differences. Then the differences are what are getting multiplied. My multiplier here was 2, here was 3. To get from 1 to 2, what am I multiplying by? 2. Okay, so I'm multiplying by 2 after I do the differences, which means this difference was 1, this difference was 2, this difference would be 4, and this difference would be 8. You with me so far? Yeah. Okay, k is not 4, right? Because that's not, I wasn't putting it in the blank. The difference here would be 4, which means that k minus 7 equals what? 11. No, k minus 7 equals 4. K minus 7 equals 4 because these are the differences. This could be 4. It's also k minus 7, which means that k is equal to 11. So if I did 19 minus 11, I get 8. All right. I know, because you were just sitting there yelling numbers out and not listening to what I was saying. The differences are in the light blue, right? And then I can tell that the differences get multiplied by 2. So this is 1, 2, this, if I knew what K was, the difference would be 4. If I knew what K was, the difference here would be 8. I had K, I already set up that this is the difference and this is the difference. If this is the difference and this is the difference, guess what? They're equal. That's where it came from. Okay? The differences are what are being multiplied. And then K equals 11. Questions? We're good? All right. If I look at this last one, then I have my equal length output value intervals. I'm adding 7. Doing differences here is not going to do me any good because e to the 10th minus e to the 7th is e to the 10th minus e to the 7th. That's like x to the 10th minus x to the 7th, right? Don't let the e's freak you out. Pretend like they're x's. It's just a variable. That's all it is. So differences aren't going to do me any good at all. But if I try to find my ratio, e to the 10th over e to the 7th, what's that going to give me? E to the 3rd. Now, I could have done that with these first two, but that was a negative exponent, and I didn't want anybody to have a brain meltdown. So basically, everything's being multiplied by e to the 3rd. And when you multiply two terms with the same base, what do you do with the exponents? You add them. So e to the negative 2 times e to the 3rd, I add the exponents, I get e to the 1st. Does that make sense? So then if I take e to the 1st and I multiply it by e to the 3rd, what's that going to give me? E to the 4th. And so that is K. K is e to the 4th. Basically, the exponents are just, you're adding 3 to the exponents each time because that's how you multiply. Okay. What questions do you have? Okay. All right, so now here, we're going to find the domain and range. But again, we're going to start off with our little pictures. So this is what a log base 3 would basically look like. That 2 is there, but it doesn't really change my bad picture. So that's it. So where do I start with the domain? 0. And I'm going to go to where? Infinity. And then my range is just negative infinity to infinity. Okay? That's without any transformations there. So my left limit, the limit as x approaches 0 from the right of f of x equals negative infinity, good. And then the limit as x approaches infinity of f of x is what? Infinity. Very good. Okay. Any questions? All right. So on B, I'm going to start off by just looking at this log base 2 part right there. That means that that was what my parent function would look like. That x minus 3, what does that 3 do to my graph? What would I do? Okay, I'm going to go to the right. X is a liar, so I'm going to go to the right 3. Right, so remember, right now, you have a vertical asymptote at x equals 0. That asymptote is going to have to move to the right 3. There's where your asymptote is now. That 5, not going to change it enough on my bad picture, but that negative does, right? That negative reflects it in the x-axis, so that means it would look like this on that side of the asymptote. Okay. You see the little thought process to kind of think through? Highly suggest you sketch it, even if it makes sense in your brain. So my domain then starts where? 3. And I go to infinity. Do I include 3? No. And then my range is still negative infinity to infinity. So then my left-hand limit, this is going to be the limit as x approaches what? 3 from the right, right? Because I can't approach 3 from the left. And this guy's name is g of x. And that answer would be infinity. Good. And then the limit as x approaches infinity of g of x, that would be negative infinity. Okay. Everybody good so far? All right. So again, here's my Original, because what's the base of that log? 10. All right, so I know by what's in those parentheses there that I'm going to have a shift. Would I be going left or right? Left, but I am not going to the left 3, okay? Because that is not the form that you look at your transformations in. That 2 would be our B value. What kind of transformation is that 2? Or horizontal what? No, dilation. It's a horizontal dilation, and it would be a compression because X lies, right? And that's fine. I can look at that way. But in order for me to figure out my translation, this has to be written this way. 8 times the log of 2 times X plus something, but it has to be factored out, and it changes what comes after that plus sign. You with me on that? Most of the time, it's already factored out for you, so you kind of lose sight of that actually happening there, but it has to be factored out. So what number is missing after my plus sign? 3/2. If I divide this by 2 to get X, I divide that by 2 to get 3/2. So I am moving to the left, but not 3. I'm moving to the left 3/2. You see the difference there and what you have to do with the transformations? Okay, so then I move to the left. We'll just know that that's 3/2, and that's fine. This 2 is that horizontal compression we already talked about. That's really not going to change. I mean, it changes values, but we don't care about the other values right now. And then that 8 is a vertical stretch, so it really doesn't change anything else. It looks like this, but always a whole lot better. Domain, so where are we starting? Negative 3/2, and we're going to infinity, and then negative infinity to infinity, right? So the left, we're going to have the limit as X approaches negative 3/2 from the right of h of X. What's that going to be? Negative infinity. And then the limit as X approaches infinity of h of X, and that equals infinity. Okay. Any questions at all? We're all good? All right. So grab your other sheet of paper. This is also going on page 68 when we're done. So I'm going to give you, listen, I'm going to give you a minute or two. I want you at your tables to discuss these graphs and these equations and put the letter next to each equation for which graph it goes with. Y'all can decide as a group. These graphs match those two together. Sorry. Yeah. All right, let's talk about this before we lose friendships. All right, so this first graph, or the first equation, log base 2 of x. Can we all agree on which graph that is? Yes. Which one is that? C. That's just your general old log, and so with the base being greater than 1, so I'm good with that. Now, if we look at the equations, the difference between these two equations, the only difference is that negative right there. If I change the sign on x, what do I reflect across? The y. So if I look at this graph and reflect it across the y-axis, I get this graph, which is A. Okay? Does that logic make sense? Always take it back to the original. So then when I look at this one compared to this one, the only difference is the negative out front. This negative out front reflects it across which axis? X. So if I take this one and reflect it across the x-axis, I get this one. Now, process of elimination tells us what that one is, but we also have to know how to pick it out if there isn't process of elimination. So there's a couple of differences here. First of all, this isn't log base 2, it's log base 1/2. So just looking at that part right there, the log looks like this, okay? But then that negative reflects it across which axis? The y. So if I take this, reflect it across y, I get this. That's why that one is D. Okay? Any questions at all? All right, now I'm going to change the directions on this next part. I should have changed it before I printed it, but I didn't, and it's going to be fine. So you have 4 more equations here. What is the base of these logs? 10. They're all log base 10. So what I want you to do here is I want you, for these equations, to sketch yourself a little graph and just tell me where the vertical asymptote is. That's all I want. You don't have to do the rest. Because if you can sketch it, you can write out the limit and do all that stuff. I'm quite confident. But the little sketch is what helps. So just make your little sketch. And you can discuss this with each other also, as long as you do it nicely. Yes, I that. But you made an effort. That's important. Okay, y'all ready to talk about these? No? Okay, I'll give you a second. I want to make sure you have time to think about it. Okay, so what I drew in red right there, that's just, since they're all log base 10, that's like my starting point, right? That's my parent function there. So here, this graph would be translated which direction? To the right one. So the graph would look something like this, right? And if you can draw that, then you can write your limit statements, right? But you got to get that so you can make it make sense. But then our vertical asymptote, that is at x equals 1. It is an equation of a line. An asymptote is a line, so it's not just 1. It's x equals 1. That's an equation of a line. We all okay on that one? All right, so then on this one, we're going to translate which direction? To the left, too, so it looks like that, and that's all that's happening. So it looks like that. My vertical asymptote is at x equals -2. Okay. So unfortunately, I get a lot of blank ones and confusion on C, but this type of thing confuses you regardless of whether it's a square root function or a quadratic or whatever. when they're written in this order, some of your little brains just fizzle out, and you try and make it way too hard, okay, to recognize your transformations. The reason that this is written like it is because this is a negative log. If that log wasn't negative, I feel very strongly that it would have been written differently. And if we write it differently, it makes more sense to you. So if I wrote this as y equals negative log of x plus 4 plus 2, that is the exact same thing. And that's the way we see our transformations. That's the way, we talk about them. But then we move that 2 to the front, and it's like your world just is coming to an end, and you have no idea what the 2 does. And you want to make the 2 a vertical dilation, but it's not being multiplied, and then I don't know what happens, and it's just terrible. So either think about it this way or rewrite it that way. But that happens a lot when stuff is given to you if whatever this is happens to be negative, okay? So just know that it's the same thing, right? So here was our original, right? So I know that this 4 means I'm going to go to the left 4. Okay. That 2 does mean I shift up 2, which does affect my numbers and stuff, but that's not going to affect my bad graph enough to matter. But that negative matters, right? It means it reflects in the x-axis, so it's going to look something like that. And then your vertical asymptote is at x equals negative 4. Even if that 2 just blew your little mind, and you couldn't draw a picture, shouldn't you still be able to figure out where your asymptote is? Because the only thing that affects that asymptote is that horizontal shift, right? Plus, we figure that out before we graph anything else, so it's not that big of a deal. All right, and then here, I'm not shifting left or right at all. I'm just shifting down 3, which again doesn't really affect my bad graph, so it still looks like that. And my vertical asymptote is where? Yep, x equals 0. Okay. Any questions at all? Those little sketches can help you wrap your mind around it for sure. Did you have some? All right, now I'm gonna change the directions down here too. We're actually gonna do very little with this. It doesn't even matter what it says. We're not plotting the points. We're not doing any of that. I just want you to look at the tables and tell me, is this function, by looking at the table, is that function increasing or decreasing? Increasing. And this one is decreasing. And you know that by looking at what? The y values. You're looking at the outputs, right? As long as the x's are in order, which they are, as x gets bigger and bigger and bigger, y gets bigger, so this is an increasing function. As x gets bigger, then y gets smaller, so this is a decreasing function. And that's true for any function, whether or not it was logarithmic or whatever. And I think sometimes y'all overthink that with your tables. That's why I just want to ask you that simple question with some tables. We don't have to worry about doing the rest. You can tell that without having to do anything else. So that means here, if the function is increasing, what can you tell me about the rate of change? Well, yeah, so if the function is increasing, what does that tell me about the rate of change?
It's increasing as well.
No. No. If the function is increasing, the only thing that tells me about the rate of change is that it's positive. If the function is decreasing, the only thing that tells me about the rate of change is that the rate of change is negative. Does that make sense to you? Those are the ones that are tied together. And I don't, without doing anything else, by just like looking at it, I don't know if it's concave up or concave down. And I mean, I could do some rate of change and figure out, but we're not gonna do all that. Okay, just think about how that works. We good? Any questions at all? Awesome.